Using a standard regression p-value for the lagged level coefficient is a serious mistake. There are several deterministic specifications. A regression with no constant is suitable only when both drift and non-zero mean are implausible. A constant allows a random walk with drift under the null. A constant and time trend permits a deterministic trend under the alternative. Adding or omitting these terms changes both the interpretation and critical values. The choice should follow the data generating question, not whichever specification rejects. The augmented Dickey-Fuller test, or ADF test, adds lagged changes of y to absorb higher-order serial correlation. The tested coefficient on lagged y still addresses the unit root. Lag length may be chosen with an information criterion or diagnostic checks. Too few lags leave serial dependence and distort size. Too many lags consume power, especially in short samples. The selected rule should be reported. Failing to reject the unit root null is not proof that a unit root exists. Unit root tests often have low power against a stationary alternative, whose autoregressive root is close to 1. Rejection supports stationarity under the chosen deterministic specification, while non-rejection leaves the evidence compatible with a unit root. Confidence sets, complementary tests, and economic context provide a fuller assessment than a binary label. A random walk with drift contains both a deterministic linear mean and a stochastic trend. Its expected value changes with time, while accumulated innovations create variance that also grows with time. A sufficiently large drift can make the graph resemble a deterministic trend, even though shocks remain permanent. This resemblance explains why separating deterministic and stochastic trends is difficult in finite samples and why regression specification matters. The Beveridge-Nelson decomposition expresses an integrated process as a stochastic trend plus a stationary cyclical component. It helps interpret permanent and transitory movements within one model. The stochastic trend is driven by the long-run effect of innovations, while the stationary component captures temporary departures. The decomposition depends on the fitted dynamics, so its components are estimates rather than directly observed economic facts. Unit root analysis is a sequence of decisions. Plot levels and differences, consider plausible deterministic terms, choose augmentation lags, inspect residuals, and compare specifications. Then, interpret rejection or non-rejection in light of power and possible breaks. A break in a stationary trend can mimic a unit root, while a near unit root can evade rejection. The next lesson adds a stationarity test, with the hypotheses reversed. The Dickey-Fuller family places a unit root in the null hypothesis. The KPSS test reverses the logic. Its null is level stationarity or trend stationarity, and its alternative contains a stochastic trend. Using both approaches can be informative because each protects a different null. Agreement is especially useful. Failure to reject either test is not agreement. It often signals weak information or competing forms of misspecification. The KPSS model decomposes Y into a constant, an optional deterministic trend, a random walk component, and a stationary disturbance. The innovation variance of the random walk is the key parameter. Under the null, that variance is 0, so the random walk is constant, and Y is stationary around the chosen deterministic component. Under the alternative, positive random walk variance introduces a stochastic trend. The statistic is built from residuals estimated under the stationarity null. Regress Y on the deterministic terms appropriate for the test and form cumulative sums of the residuals. If the residuals are stationary, these partial sums remain relatively controlled after scaling. A stochastic trend makes them wander systematically. The test aggregates the squared partial sums and divides by an estimate of the residual long-run variance. Long-run variance estimation matters because residuals may be autocorrelated and heteroscedastic. A short or long lag truncation can materially change the KPSS statistic. The deterministic specification also changes its limiting distribution and critical values. A level stationary test and a trend stationary test answer different questions. Software settings should therefore be chosen explicitly and reported, not accepted as invisible defaults. KPSS. Critical values are non-standard because the statistic converges to a functional of Brownian motion under the null. Large values lead to rejection of stationarity. This direction is opposite to an ADF test, where a sufficiently negative statistic rejects the unit root null. Remembering the null is more important than memorizing a critical value. Log prices are natural candidates for I1 behavior, while log returns are typically closer to I0. The comparison also asks whether conclusions change with the sample window. For log prices, the ADF regression includes a drift, and the KPSS analysis considers both level and trend stationarity. For returns, the ADF regression is run without a deterministic term, while the KPSS null is level stationarity. These choices reflect different empirical scales. A deterministic term appropriate for a price level may be unnecessary for a short horizon return series. In RA, the unit root workflow removes missing values, selects the deterministic specification, includes an augmentation lag, and may use an information criterion for lag selection. The KPSS routine then estimates the long-run variance using its chosen lag rule. Reproducibility requires reporting the package, sample dates, lag settings, and transformation. Merely stating that a unit root test was performed does not identify the actual test. For SPY log returns, the ADF test strongly rejects a unit root in both the full and recent samples. The full sample statistic is about -60, and the recent sample statistic is about -11.3, both far beyond their 1% critical value.